Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, with that, I'm very happy to welcome Alexey Loganov here from University of Wisconsin-Madison, where he's done his PhD work with Thomas Reps. He's worked on abstract interpretation of programs with heaps, and he's looking at how to do things like automated abstraction and refinement for programs with heaps, and we look forward to hearing about it.
Thank you.
Thanks.
Thank you. The National Institute of Science and Technology estimated that about $60 billion annually is wasted because of software errors. You've probably all seen this number many times. This happens to be just a little bit below the combined net worth of Bill Gates and Sergey Brin, a co-founder of Google. However, if that doesn't sound like much, it's also about 5 times Microsoft's net income for the last complete fiscal year. And the same estimate, the same study also estimated that about a third of the cost could be saved through the use of better tools for software testing and verification. Now, do we really need tools? Can't programmers simply write better code? A survey at Hewlett-Packard, which studied about 29 different projects, discovered that on average, programmers produce about 26 lines of code a day. A separate survey asked people how many lines of code they can write and be confident about their correctness. Now, that number was only about 7, and that's that gap of 19 lines that worries me. The problem that I'm trying to address is the analysis of heap manipulating programs. Heap data structures are everywhere because they're flexible, they're easy to use, and they're very space efficient. Take, for instance, the Java util package and its widespread use. However, they harbor subtle bugs heap manipulating programs harbor subtle bugs because of dynamic memory allocation and destructive pointer assignments that are very difficult to understand and reason about. And it is exactly these features that make it difficult to reason and analyze programs that manipulate the heap. Because dynamic memory allocation, for instance, often results in null pointer dereferences or unbounded allocations, resource problems. And destructive pointer assignments often create all kinds of complicated aliasing relationships that make it very difficult to reason about a data structure. And the holy grail is to find good abstractions of linked data structures that would allow us to statically verify their properties. And in this regard, I'll be discussing 2 of my main contributions. One is automatic abstraction refinement, which was presented at CAV last year. And this work established a new link between program analysis and machine learning. Namely, I showed that ILP, Inductive Logic Programming, can be used for creating abstractions of linked data structures. And refinement via ILP actually goes beyond merely forming Boolean combinations of existing predicates. And the second contribution, which I will hopefully find time to talk about, but I might skip and talk to people in private about it, is finite differencing of logical formulas. And that work established connections with databases and descriptive complexity in an automatic method for maintaining refined abstractions. So I'll start by discussing the need for verification tools. Then I'll give an overview of 3-valued logic analysis that is the foundation of my work. And then the 3 bullet points in yellow are my contributions. First, learning the use of machine learning for abstraction refinement, and finite differencing as an automatic technique for maintaining abstractions. And then I'll discuss a few case studies. Most likely, I will just quickly discuss Deutsch-Schur weight and automatic verification of its total correctness. And I'll conclude with a summary of contributions and discuss some possible future research directions. At the high level, there are 2 main approaches to software quality: testing and verification. And testing, as far as I'm concerned, testing suffers from the drawback that it cannot cover all possible behavior, so it can only be used to find bugs and not guarantee correctness. Verification, on the other hand, is the process of applying formal methods to check a program against a specification. Covers all possible behavior, so it can actually guarantee correctness, of course, with respect to a particular specification. And so from now on, I'll be talking about verification via static program analysis. Examples of this are abstract interpretation, data flow analysis, model checking, all of these are instances of this general framework which attempts to compute properties of all possible execution states. And of course, this is undecidable in general, but undecidability can be sidestepped by over-approximation. And here's how we can visualize this. If this box is the universe of all possible states, and we have this circle that represents all states that a particular program that we're trying to verify can reach, and we have some bad states, we attempt to iteratively approximate program states, and we have a way to detect when we have an over-approximation of all possible program states. And if there's no overlap with the bad states, then we can safely say that our program satisfies the specification which rules out the bad states. And so, once again, static program analysis can establish conformance to a specification if it over-approximates the set of possible states that can arise. Now, over-approximating an infinite set of states with a finite one requires abstraction. And abstraction really is composed of two elements. First, it's a mapping of concrete values onto abstract ones. For instance, in a simple example, let's take all even integer values and map them to the abstract value even. Take the odd values, map them to abstract value odd. And then the second component is a transformer, something that's known as a transformer, which is the semantics of operations of your program in terms of abstract values. So for instance, if we care about multiplication or subtraction, we can talk about what it means to multiply or subtract quantities that can be even or odd. So for instance, x times y is even as long as at least one of them is even. And x minus y is even if and only if x and y have the same parity. Now, it's, my work in automatic abstraction refinement and finite differencing kind of represent these two concepts. Automatic abstraction refinement as a method to obtain a mapping, and finite differencing is a method to obtain semantics of operations via abstract values or transformers automatically. So how can we make use of this? For instance, if we have this tiny little program, we don't know what happens after the declaration, but we can still reason about this program with some degree of precision. For instance, we say that 2 is an even number. We replace like this. 3 and 1 are odd. Anything times even is even. Now we replace x with even. Even minus odd is odd. Odd times odd is odd. So whatever happens in this segment here, we know for sure that at the end x is always even and y is always odd. And so this is an example of over-approximating all possible behaviors. Now, unfortunately, programs are not as simple as what we just saw. And the main complication that I'm concerned about is the heap-allocated data structures. And we need to have an understanding of what happens in the heap for many different reasons. For instance, for static safety checks. Can there be a null pointer dereference? Can there be a memory leak? Can there be a data race, et cetera, et cetera? For that, we need some static safety checks. For that, we need some information about the layout of the heap. For optimization or parallelization purposes, for instance, if we know that 2 threads have no data, reach no data that is shared, then methods on these threads can be executed in parallel. Or from program verification and understanding, simply to figure out if a program satisfies a partial correctness specification, or to figure out what the layout of the heap may be. So all of these require some information about the heap. Now again, why is heap analysis difficult? First, dynamic storage allocation, which means that there is no bound on the size of runtime data structures. So this makes our task of obtaining a finite abstraction, a finite representation of all possible states, that much more difficult. And second, destructive updating through pointers. An assignment such as p.next gets q produces complicated aliasing relationships among the structures that p and q may point into, and that these may make it very difficult to reason about the programs that have assignments such as this. So now let me give you an overview of the three-valued logic analysis framework on which I built my work. The basic idea is what we call a formalization of ... When you're faced with a question of whether a piece of code that you wrote that manipulates the heap does it correctly or not, you will often do this by simply symbolically interpreting the steps of the algorithm on a little picture. So here at left we have a simple algorithm that actually all it's designed to do is let t point to the end of the list that x points to. So t for tail. You might start out by drawing the beginning of the list x. Let's say we think that there's at least one element. And then stepping through the algorithm. If x is null, well here we're saying x is not null. We move forward. T gets x. Simply draw an arrow from t to what x points to. While t.n not null, Well, we need to see if there are more elements or not. Suppose we consider the situation where there are more elements. T gets T dot next dot n. We move T one step forward in the list. Again, well, let's suppose there are more elements. Move T over. Let's suppose we decided we're fairly satisfied. We just have one more element. Move T over. Notice that at this point, there's nothing important that distinguishes these two elements one from the other. And so we could actually summarize them together and show them with a single kind of summarized dot, 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 and have some degree of confidence that whatever happens, at the end, T will point to the end of the list, and there may be any number of elements between X and T, if we were methodical about our exploration of the possible list. And so the basic idea is to use shape graphs for state space exploration, and we're abstracting out what's not important with dot, 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 and focusing on the important parts and not summarizing them. And so this is the framework that was introduced by Muli Sagiv from Tel Aviv University, Tom Reps, my advisor from Wisconsin, and Reinhard Wilhelm from University of Saarbrücken. And in this framework, program states are modeled by logical structures, and individuals in these structures represent heap elements. And there are special summary individuals that can represent collections of elements. So these summary individuals correspond to these dot, dot, dot groups of nodes. And the unknown value 1/2 is used to represent uncertain information. And this will become clear. I just give you some advance warning of what's coming. Now I need to tell you, how is it that we decide when two elements should be grouped together into a single dot, dot, dot group, so to speak? Here at left, we have a concrete structure that represents a list of linked 4. There are 4 elements in the list, U1, U2, U3, U4. Program variables X and Y point to the very first element, and these are the N, or next links. Okay? We can represent this using logical relations. For instance, we can represent the information about X and Y via unary logical relations X and Y. So the fact that X and Y both point to U1, as follows, can be represented with these two 1s here to indicate that X and Y point to this node U1 and to nothing else. And to decide what nodes should be grouped, we'll look at the distinct vectors of unary relation values. There are 2 distinct vectors, 1, 1, and 0, 0. This tells us that, given what we've seen so far, U2, U3, and U4 are indistinguishable. They're indistinguishable according to the unary relation vectors. And so we will group them into a single summary individual, which we'll call for convenience U2, 3, 4. And so the 1, 1 that from U1's values gets carried over, and 0, 0 gets copied over from U2, U3, U4 to U2, 3, 4. And pictorially, this can be represented as follows. Again, we have individual U1 to which X and Y point to, and then we have the summary individual U2, 3, 4, and summary individuals are indicated with double circles. We're saying, they may represent more than one individual. Now I need to tell you what happens with the next links, or N links. Right? So these can be represented via a binary relation, N. So here we have only 3 non-zero entries. They correspond to the 3 edges. So U1 points to U2 with its next field. So we have this entry 1 from U1 to U2, etc. Does that make sense? So this is a representation of our next, or N, fields. And now we need to know what this should look like in a table that has only U1 and U2, 3, 4. Well, this is easy. We simply draw a quotient. This division into U1 and U2, 3, 4 introduces a quotient on this, on this matrix. So the value for U1 is copied over from here, and indicates that even in the abstract structure, we know for sure that U1's next field does not point to itself. The value from U1 to U2, 3, 4 here is obtained by taking the joint, or grouping the values from U1 to U2, U1 to U3, and U1 to U4. And so it represents the next edges from U1 to any one of the nodes, U2, 3, or 4, and it's 1/2, because U1 points to U2 with its next field, but it does not point to U4. So this is the only safe representation. Then U2, 3, 4 to U1 is 0. None of U2, U3, or U4 points to U1 with their next field. And U2, 3, 4 to itself is 1/2. Again, because, for instance, U2 points to U3 with its next node, the next field, but not vice versa. So a safer approximation of what the n value is from U234 to itself is 1/2. So we do not use, for us, 1/2 simply means maybe. It's not a numerical property of, being 1/2 likelihood. There's a way of looking at it in probabilistic terms, but we simply say 0 means definitely the absence of information, 1 definitely presence of information, 1/2 is possibly this, possibly that. So, yeah.
So in this logical structure at the bottom, you actually, unless you add other constraints, you could have a heap in which U1 points to the ball, 3, U2, 4 simultaneously, right? Because you haven't.
You could, yes, absolutely, absolutely.
Actually added constraints.
Absolutely.
That there's only one
right.
pointer.
Absolutely. There are many different, so first let me show you how these 1/2s are represented. So we use dashed edges. So U1, so this 1/2 is represented by this 1/2, by this dashed edge, and this 1/2 is this dashed edge. And you're absolutely right. It represents a situation in which U1 points to every single one of the nodes summarized by U234. It also represents a situation where this guy contains a cycle. This guy represents a whole cyclic structure. So there are many different things that it could represent, and the task is to find good abstractions that accurately represent the information we actually care about. But you're right, as is, it represents a lot of things that are a lot more than simply lists. But in particular,
in fact, it represents infeasibles in that sense.
Yes.
If we really think it's then U1 only has one next.
It cannot.
Only ever point to
Exactly. So that's one of the things, and it's one of the simplest types of information that we build in to avoid this. But yeah, absolutely. So in particular, it represents things that cannot actually arise under any circumstances. Yes. Mm-hmm.
You said that you point to U2, but not vice versa. Therefore, you put in 1/2.
Right. Both are good reasons. Both actually are real reasons for this. And if we had a definite one edge here, that would represent not simply that every single node has an outgoing edge. It would represent that every single node in this group points to every single other node. One is very different. You're right. It's a subtle observation. It's a very good point. But my original reason is also correct, although yours is good as well.
And that means that in the concrete graph that you have, you could actually have more than one outgoing edge.
Right. So I can. So this can be all constrained further via some constraints and via additional relations that we maintain. Right. So. And can you repeat the example?
The simple answer is that this isn't limited to lists. You could have multiple.
Right. You can have multiple. Next, you can represent trees. You can represent whatever you want. And maybe if I represented trees, I would have, instead of a single n binary relation, I would have two binary relations, left and right. Right. Precisely. Yes. So for each pointer field, and for each program variable, they can point to only one thing, and so that information is built into the analysis.
So that suggests that into a summary node, there could never be a solid edge pointing to a summary node.
That's true. For a given single, that's precisely correct. Unless I say, accidentally, I find out there's a definite edge here, and that simply tells me that that summary node really stands for only one node, and that happens to be an self-loop. Yes. Very good point. Yes. So when you think of abstractions, this is an image that comes to mind. Is it a good abstraction? Is it a bad abstraction? This is you might recall this from Alice in Wonderland. This is a Cheshire cat that disappeared, leaving only a smile behind. Well, this is all that's left. You're not quite sure if this represents a cat or something else. You have no idea. What we're trying to do instead is something along these lines. It has a tail. It has a leg, maybe more. Who knows? It has some teeth. And this Picasso-like rendition is certainly certainly gives you a sense of what is being represented or abstracted, if you will. So again, the framework uses logical structures to represent the possible program states and has has individuals representing heap elements and has these special summary individuals. And value 1/2 represents uncertain information. The semantics of program statements is expressed in first-order logic extended with transitive closure. And this will show up a little bit later. And the basic idea is to find all possible abstract structures that can arise at any program point. And this is done via the technique known as abstract interpretation. And this is what's implemented in the TVLA tool. Now, you might have noticed that canonical abstraction, just as Tom was bringing up this issue about the imprecision harbored in these abstract structures, canonical abstraction is actually a family of abstractions. Given a particular set of unary relations that you use to group individuals, you can have different degrees of precision. And so the goal is to find a sufficiently precise one to answer a particular question. Let me just explain this using this example of insert sort. If it's given a linked list, it starts by setting pointer variable r for right to different elements in the outer loop. And for every value of r in the inner loop, we use pointer variable l for left to point to different elements of the list until, and it moves forward until it detects that r's data is less than l's data. This is an indication that r's target should be moved just prior to l's target, resulting in the following list. Okay, this is basically all there is to insert sort. What we would like to be able to represent when we're talking about insert sort is something like this, that we have a structure in which x points to the start, L points somewhere further, and R points somewhere further yet. And it is important to distinguish nodes in these different groups because, for instance, these nodes, actually all of these nodes, have not been put in the right order. All of these nodes have, but these nodes have not been compared with R yet. So it would be nice to be able to have an accurate representation of this. However, canonical abstraction, given what we've seen so far, which is unary relations only based on values of pointers, cannot distinguish anything about these dots. None of them are pointed by any program variable. So as offhand, canonical abstraction will say, okay, all of these are a single summary individual. And we have no ability to distinguish nodes that have been already sorted from those that haven't. How can we fix this? Like this, for example. We can introduce additional properties based on reachability from program variables. All of these nodes are reachable from program variable R, so we can give them a special property R sub R for reachable from R. So it shows up here. All of these nodes are reachable from L, so we get RL. And these nodes are, and all of the nodes are reachable from X. So these properties based on reachability from X, L, and R allow us to fully separate every single group of summary nodes. Okay? And of course, this is only a pictorial representation, only a rendition of what we manipulate underneath. What we manipulate underneath are collections of relations. Think of them as database relations or whatever you'd like. For instance, we have these unary relations X, L, and R that represent what program variable X, L, and R point to. We have the binary relation N, which represents the next fields. And these are what we call core relations. They directly correspond to what the program manipulates. They have a direct meaning, direct semantics corresponding to the program statement semantics. And then what we introduced later are these reachability relations. They can be defined in terms of core relations. We call these instrumentation relations because they kind of instrument the structure with additional information. And think of them instrumentation relations, derived relations. They're very similar to database views. So we can define them in terms of the core relations using first-order logic with transitive closure. So for instance, node V is reachable from program variable R if some node V prime is pointed to by R. And from that node, we can follow an end path to our node V. Okay? Yes, Sumit? No. So this is a very good point. We don't actually need to write down invariants. We need to write down something slightly simpler. We need to write down important node distinctions, such as reachability or something like that. And then TVLA automatically synthesizes invariants via the process of abstract interpretation. So we only need to write down node distinctions, and that's simpler than true invariance. And then additionally, my work on abstraction refinement tries to introduce new node distinctions or relationships automatically as well. Very good point. So again, so the main mechanism to tune the precision is to equip it with additional instrumentation relations. And again, what we're trying to do is if when we're approximating all our program states, we've got this big approximation, but it's actually bad states, maybe we're a little closer, we have an overlap, this is a false error report. How can we distinguish it from this situation? Well, so our mechanism for that is the addition of new instrumentation relations. And there the hope is that we'll over-approximate our program states less so we can actually detect that the program still satisfies our specification. So now let me start talking about my work, which is the use of learning for abstraction refinement. And of course, we'll start with some motivation as well. The basic problem is that devising good analysis abstractions is very hard because of this well-known precision and cost trade-off. If the precision is, the abstraction is too coarse, then the answer is usually unknown. And if it's too refined, we will quickly run into prohibitive time or space costs. And so the Holy Grail is an automatic method to identify abstractions. And this is where my contribution on refinement fits in. The basic idea is to start with a simple and cheap to verify abstraction and then successfully refine it in an adaptive fashion. Very similar to all the work on abstraction refinement in the model checking community. The challenge for us is new, however. What we need to do is find suitable instrumentation relations, which define some interesting distinctions between nodes or maybe relationships among nodes. And that's different from the work in the model checking community. At certain points during the analysis, the abstract state may hold some information that may get lost because of abstraction. And my observation is that we can use machine learning, namely inductive logic programming, to learn these properties that disappear because of an abstraction step and use these properties to define new instrumentation relations. Again, recall insert sort, all it does is runs around with the R pointer in the outer loop. The L pointer goes from the start to the first point where R's data is less than L's data, and that's when we need to move R's target. It has an interesting property called stability. I'll just illustrate it on an example, and then it'll be easier to talk about it. In the following list, we have note that we have two elements with identical data values, identical keys. The first configuration of L and R for which some action has to be taken is as follows. And this is an instance where R, again, has to be moved before L, resulting in the following list. The next time anything has to be done, L is here, R is here. Again, we need to move R's target just before L's target, and we get the following list. Note that the relative order of the two elements with equal data values has remained the same. And it's not a coincidence. It is, in fact, a property of insert sort, and it's called stability. The basic idea is relative order of elements with equal data values is unchanged. And this property is important in many settings. For instance, if you're doing a sort on multiple keys, you might start by sorting on a secondary key and then sort on a primary key. And if you use a stable sort, you have a guarantee that the secondary key order will be preserved. And the idea of radix sort is actually an extension of that thought. You can think of radix sort as being a n key sort, in case you're familiar with radix sort. How can we express that in TVLA? First, we use an abstraction of numeric properties. And I should warn you that TVLA can, in fact, talk about numeric properties directly through the work of my office mate, Dennis Gopan. But for my work, I've been usually abstracting them and treating them using first-order relations to represent numeric properties. So for instance, DLE V1, V2 says the data of V1 is less than or equal to V2. So here, yellow edges indicate all the instances. First of all, it's a reflexive relation, so there's these self loops. And also, for instance, 6 is less than 9, so this node will be related to this node. Okay? So it's a simple encoding of the numeric ordering. Another relation I need is transitive closure. So Tn v1 v2 is simply the reflexive transitive closure of n, or next, the order in the list. So it simply says v1 precedes v2 in the list. And additionally, it has self loops because it's the reflexive. So you see the yellow edges moving to every, showing a path to every node forward from a node. And finally, we need the initial state of Tn, reachability on entry, to be able to discuss how reachability changes, how the order of elements changes. And so the property can be stated as follows. For all pairs of nodes V1, V2, if they have equal data values, and here I write down, DLE V1, V2 and DLE V2, V1, so inequality in both directions. And initially V1 preceded V2, then at the end V1 will precede V2. So this is a simple way to state the stability property. If we use only the relations that we've seen so far, which is the pointer variables, reachability, and things like that, it's not sufficient to establish the stability of insert sort. You're starting to see a picture. It's never enough. You always need more. And it's because we're losing the data ordering between what L points to and what R points to. Let me show this on an example so it's not so abstract. So this is a structure that arises just prior to, I'll explain everything in due time. This structure is a visualization of what arises at TVLA during the analysis just prior to the statement L gets X. So this happens when you reset the left pointer to point to the start of the loop again for the next iteration of the outer loop. And what happens is we have the structure with 5 nodes. There are various program variables X, L, PR, and R that point to various places. And no nodes need to be merged yet because they all have different properties according to reachability or pointer variables. This guy's pointed to by X, this guy's pointed to by L, this guy's pointed to by nothing, etc., etc. What happens when we assign X to L? L, first of all, and by the way, so these are the next edges, and all unlabeled edges, all these curved edges, represent the DLE, data less than or equal relationship. They're the numerical ordering. So what happens is L will disappear. Now U2 and U3 are no longer distinguishable according to any characteristics we're maintaining right now. Neither one of them is pointed to by anything, and both of them are reachable from X and from nothing else. However, and so they'll be merged together, and the DLE relation, the data less than or equal relation, will get the subblock corresponding to U2 and U3 and convert it to a single 1/2. Note that we have this interesting upper triangular matrix here, or form of the matrix, which indicates that every node up until U5 has already been put in the right order. This is what these ones mean. Every node is related via DLE to every node further than it, except for U5. And so this corresponds to the following definite edges. So we're saying all these guys are already in the right order. In particular, there's the same matrix for the U2 and U3, corresponding to these definite DLE edges. So we're saying U2 and U3 are in the right relative order, but this all gets lost when we combine U2 and U3 because of this pesky little 0 here. So what happens is, ignore what happens outside. This is the submatrix corresponding to U2 and U3. We start out with a nice little list that says, well, U2 and U3 are in the right order. Then we summarize U2 and U3 and get a summary node with a possible DLE edge onto itself. We have no idea what happens. Next time when we look into what the summary node represents, the best we can do is say, well, anything is possible. There's halves here. We can do a little bit better, but not much better than that. And so this point is what I call an information loss point. The abstraction lost some key information for me that is preventing me from solving the problem, from verifying the problem. And it is this point that I identify automatically and apply machine learning to try to preserve a relationship that disappears. The basic idea is the following. First, as you saw, this submatrix becomes 1/2. But what if we had some other relation? I'm not telling you what it is yet. What if we had some other relation that had 4 1s here? Well, the combination of them would still be 1. First, how can we learn such a relation? I'm not telling you what it is yet, but how can we learn it? Well, we can learn it via inductive logic programming. And it's a technique that takes a set of positive example tuples E+, a set of negative example tuples E-, and a logical structure. And it finds a first-order formula such that all positive examples are satisfied or covered by this formula, and no negative ones are. And actually, if you look at the ILP literature, it's usually in terms of learning a Prolog program. But really, think of a Prolog program as a kind of basically a first-order logic formula that that can also have recursion. That's actually a very interesting point. I have some ways to possibly learn reachability automatically, which is transitive closure formulas automatically as well, but that's pretty tricky. So I usually prevent myself from learning recursive relations. And also, it does not allow alternation of quantifiers. However, that's easy to extend. I can actually learn formulas that alternate. In an extension that I implement, that I can learn formulas that alternate existent for all quantifiers. I haven't needed that yet, though. So now, I'm not telling you what the algorithm is, but it's a simple algorithm based on trying to cover the tuples, trying to cover the positive tuples and exclude the negative ones using some existing relations. And here, if we're trying to learn this, if we're trying to get 4 ones, really that amounts to 4 positive examples. U2, 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 U3. Yes? In what sense? Right. So there. So the. I have relation symbols. So I don't have function symbols. I could introduce function symbols, but we don't have them in TVLA. I have relation symbols. So nullary, unary. Right. I don't have function symbols. Right. So I don't have function symbols. I represent functions via binary relations. And so I get around that issue, I think. Yes, Sumit? I'm not saying that there should be a 1 in place of 0. I'm just saying that if I have these 4 ones, then I'm able to maintain precision in this relation. Because when I abstract it, I still get a 1. Because the 4 ones combined give me a 1. I simply know. 4 ones together are still a 1. The question is, how will that help me? And I don't know. I can see that I can perform a test to figure out that a relation I'm about to learn, that it will be useful later. That's not a guarantee that it will be that it will eliminate my counterexample, so to speak. But I know that it's moving me forward. No, but I can maybe show it to you, or if we have time, maybe at the end I'll show it. I have a good high-level. It is. That's a good question. It could be very expensive. It is exponential. I mean, you're trying different kinds of combinations of literals, but in general, it's fast. So in general, it's not an issue, but it is looking at an exponential state space. So, but there are many optimizations. There are many techniques. It's such a vast field of work that they are normally concerned about trying to learn something from huge amounts of data. That talks about some biological data or something like that. And so they have, if you think of individuals, they have hundreds of thousands of individuals. That's my rough guess, rather than 4 or 5. So I really don't believe that it will ever be an issue for my size. Yes, Tom.
Well, I just think that we should get.
Okay.
I know there's a lot of build-up.
Right.
I want to make sure we have time for constructors.
Right. So.
No, of course, but also we have a time constraint to it. I'm not saying don't ask questions. I'm saying we have a budget and we have to.
Okay. So basically, we look and we try to cover these ones, and literal DLE here covers these 3 tuples. Literal not TN covers the remaining tuples. We negate this 0, and so this formula, which happens to be a Boolean combination of things, but it's not always true, DLE or not TN has exactly this shape. Now, how does this help us? Well, actually, DLE or not TN is exactly TN implies DLE, which captures the transitive ordering between elements. It says that if V1 precedes V2, then V1's data is less than or equal to V2's data. And the addition of this allows us to verify stability. I'm sorry? The data comes from the abstraction step. So just before we perform an abstraction, we see that we're losing precision in a DLE. I'm sorry? No. No, there's an automatic check that says DLE and TN are losing precision. Can we learn something about them, preserve some information that will disappear? Because I see that the zeros and ones are getting combined into a half. The algorithm sees. It's all automatic, yes. Yeah.
I mean, I was with DLE or not DLE.
Sure. That's one of the many things. So that's easy to rule out based on some normal ILP heuristics. But there are multiple formulas that can be learned. And the key is that, first of all, no formula is wrong. We may learn formulas that make us maintain some extra information that doesn't help us. But there's no possibility of learning a wrong formula, just a useless formula. And I have some heuristics that will actually boil down the answer to only two. In this instance, I'll learn only two relations. Actually, it will be DLE implies TN or TN implies DLE. And they don't cost me anything extra. Good question. So in the interest of time, I think I'll skip the finite differencing. Oops. Let me just skip over a few slides. I think I will probably talk to a few of you about the finite differencing technique, which is an interesting technique for automatically obtaining transformers. But we're a little short on time. I'll also probably just talk about one interesting example that I verified automatically with TVLA. Oop, that's not it. So some of you may know about this Deutsche weight algorithm, which is a way to traverse a tree in a constant space, meaning without the use of a stack at all. And actually, the particular variation of the algorithm that I'm looking at is called Lindstrom scanning, which further does not use any tag bits. Something like this is important when you're trying to, for example, do garbage collection. Because you already are running out of memory, so then the last thing you want to do is start performing traversals of linked data structures and creating new activation records for every visit of a new node. And so it's important to have a very low cost and ideally, constant space algorithm. And it's considered a key test for formal methods, but it's been very hard to verify automatically. Prior approaches were proof-based, and that was very laborious. For instance, the J-based proof by Richard Barnett took 152 pages to write down. And I used TVLA to show total correctness, which is partial correctness, meaning that the original tree is restored and that the algorithm terminates. So first, let me tell you roughly how it works. The basic idea is to perform rotations of pointers every time you visit a node. So every time you visit a node, you repoint its left and right pointers in such a way that the pointers form a stack in some sense. They kind of simulate a stack of incompletely processed nodes. And the left side shows almost the entire algorithm, or at least it shows the most important part. So the pink edges here represent what the former, the initial left and right edges. And the key question is, do we restore the original tree after the traversal? And this is the part that's very difficult to verify automatically. And so here we just step through the algorithm a little bit. We move next. We save the former left child of cur. Cur left gets repointed to what right used to point to. Cur right repoints to before. And so now see, we're kind of creating this stack of incompletely processed elements. Now we move forward to say prev gets cur. Cur gets next. So we visited this node once now. We kind of maintain these visit counts. And now we move on to traverse the left subtree. When we're done with the left subtree, actually we'll magically come back up and we'll start pointing to Kerr again in the following configuration. I won't step through everything closely. I'll just let the animation play through. But basically what's happening is we're performing one more rotation of pointers and then moving forward into the right subtree, surprisingly. And then we will have visited this, we have visited this node twice. On the final visit to the node, we'll perform one more rotation of the left and right pointers. And look at that. We reestablished the original left and right pointers. So we're, at least with respect to what this node cares about, we have reestablished its left and right pointers, and this is true for all nodes. And now, Kerr points up. So now we're starting to move back up the tree. And so, so this very interesting algorithm. And if every node is in fact visited 3 times, the 3 times we perform a rotation of the left and right pointers until we reestablish the original values. And we're guaranteed that we visit everything and we terminate. Now, to be able to verify the correctness of Deutscher weight, we need to track these these relationships among, well, first of all, the correctness basically is expressed as the fact that left and right pointers are restored to their original values. And so this can be stated as for all v1 and v2, left is the same as initial left. And for all v1 and v2, right is the same as initial right. There's also the property that every node is visited, and that's I fold that into the termination argument. And so I simply define a handful of simple instrumentation relations, such as for nodes v that have been visited exactly once, I care about whether their left children are what their right children used to be. And so 6 simple distinctions like this are sufficient to verify it. Now for termination, I ensure that progress is made on every loop iteration by first taking a snapshot of the visit counts of nodes at the head of the loop. And then at the end of the loop, I make sure that one node's visit count is incremented and all other nodes maintain the current visit count. And the fact that no node has a visit count of above 3, actually every node has a visit count exactly 3, tells me that the algorithm terminates and is guaranteed to terminate and it visits every node. And TVLA explores over 200,000 different abstract structures when trying to establish the correctness of this. And at some statements, there are as many as 11,000 distinct abstract configurations that need to be maintained to be able to verify the property. We see structures up to size 15 and at some intermediate steps up to size 21. So it kind of gives you the idea of why it's so complicated to verify by hand, because there's so many distinct configurations, even when you perform abstraction, that need to be maintained separately. Interestingly, TVLA showed me many more properties than I expected. At first, I wasn't realizing that every single predecessor is a node is in state 1 or 2, depending on exactly which side you went on and things like that. And so it's pretty fun to play with TVLA sometimes and tell you something you don't know about the algorithm. Well, I guess I'll just conclude by saying that I briefly talked to you about the use of about automatic abstraction refinement via machine learning, namely that inductive logic programming can be used for creating abstractions, and it's a new technique that actually goes beyond obtaining Boolean combinations of existing relations. And I didn't tell you about finite differencing of logical formulas, but this work provided a technique for automatically maintaining abstractions, for automatically computing transfer functions incrementally. And it borrowed some from the fields of databases and descriptive complexity, for example, to show how to maintain transitive closure and reachability without recomputing transitive closure or reachability, meaning how to maintain transitive closure in first-order logic. And that's an interesting result that made it possible to have precise analysis for trees, lists, cyclic lists, acyclic lists. We're automatically verifying that reversal behaves correctly on whatever kind of list you give it, maybe a cyclic list with a handle, and things like that. I extended TVLA with these techniques and validated my approaches on a few programs with destructive pointer manipulation. And one of the more interesting results is the verification of total correctness of Deutscher weight. I've also worked on interprocedural shape analysis in the presence of recursion. This was published in SAS. There, the idea is to use the concept from my abstraction refinement work called two vocabulary structures to represent, to provide summaries of shape manipulating procedures. In this way, you can have an encoding of what you can have summaries of procedures that are recursive that manipulate trees, lists, etc. Semantic minimization of propositional three-valued logic formulas, quite a mouthful, is an interesting result that I don't have time to get into, but there's a simple algorithm for obtaining a minimal, in some sense, a most precise three-valued logic formula in some sense. I also worked on a static data race detection algorithm that was later folded into a dynamic data race detection algorithm that had a very low overhead and very few false positives. So instead of erasers 10 to 30 times overhead, for instance, our algorithm had overheads of only 10 to 40%. And then I also worked on debugging of C programs via runtime type checking that was later used for for detecting possible security violations. I had some little graphic of how my contributions fit in that I'll just go through quickly. In the future, I believe that software quality should be our highest concern. And I think we need better tools for program verification, debugging, reverse engineering, program understanding, anything related to the quality and understanding of software. And the key observation that I made when I was looking at the use of machine learning for program analysis is that I believe that the best descriptor of a program's behavior is not the comments, it's not the annotations, and not the specification. It's really the program code itself. So a theme that I might carry on is mining information from program code by learning. And the exploration techniques of TVLA and the state space search of ILP actually could be used for high-level specification synthesis, or maybe even automatic test case generation. A sample application is to take a bug fix, use the fixed and buggy versions of a program as sources of positive and negative examples in order to construct regression tests for a bug fix. Or if you have a proposed code change, maybe you can automatically synthesize a high-level specification of what this change really will amount to before you actually make the change. Also, whenever you're faced with legacy or binary code, it's very difficult to say whether that code has some problems such as unsafe memory operations, memory leaks, deadlocks, information leaks, even infinite loops. Is something that we may be able to address. And something that I'm looking at is the use of TVLA and a tool called CodeSurfer x86 for extracting modules that manipulate the heap and try to analyze them separately in a standalone fashion and get definite answers about problems such as this in binary code, in x86 code, or in C code, for example. TVLA is very expressive and flexible, and so it can be a good fit for all kinds of other verification tasks, such as concurrency. Instead of thinking of heap elements as individuals, think of locks, threads, objects as being individuals that are related by things like logged by, held by, etc. Information flow, there are ways to analyze more subtle information flow that arises in dynamic data structures via TVLA. Privilege separation, maybe we can get better techniques for privilege separation by not ignoring what happens in the heap or not making conservative assumptions. Cache coherence protocols, think of cache lines and processors as individuals. So there are all kinds of different directions that TVLA could be taken in. There are also some lower level potential for collaboration that I'd like to explore in the future. One extension of ILP or of the particular ILP algorithm that I implemented is it creates nullity formulas that can differentiate among distinct logical structures. What this allows me to do is introduce nullity formulas that could serve potentially as predicates in a predicate abstraction setting, and they allow you to prevent the merging of structures with different behavior, different properties, and separate them in some sense. In proof theoretic verification systems, we could obtain some automation by learning invariance. Many people here have looked at this question. And the use of TVLA and ILP may get new leverage on this problem. TVLA could also serve as a mechanical proof checker in some instances. I'd like to borrow something from decision procedure approaches to check the feasibility of counterexamples constructed in TVLA. So that's the direction that I could borrow from. And also for scalability of TVLA, for instance, applying ILP at different points in the program may allow me to learn different abstractions that carry different amounts of precision at different points of the program. So there's potential to use ILP to create parsimonious abstractions, as they're known from the BLAST work in TVLA. And also BD representations of first-order relations as a way to maybe increase the scalability of the system. I just want to conclude that TVLA is widely available, as most of you probably know, and it's received contributions from Tel Aviv University, Wisconsin, Saarbrücken, INRIA. This is my colleague Bertrand Janet, with whom I worked on interprocedural shape analysis, IBM Research, UMass, et cetera, and people at Berkeley and MIT are using this tool to create some new applications, combine predicate abstraction with TVLA, for example. So I know I kind of hurried at the end. I apologize for that. Hopefully I'll have time to explain things a little bit in more detail. Yes, Tom.
Do you have the slides?
Yes, yes, yeah, I'd be glad to. Yeah. Right. No, it's okay. I kind of I'd rather be finish a little bit early and then get a chance to go through things again, as opposed to be kind of. Yeah, actually, I have a pretty high-level explanation of it that, and I have no control of my laptop. That might give a good flavor of what it's like. Okay. I'm hiding things so you don't see that how many slides I have. Yes. Up to. So the basic problem is, if we introduce instrumentation relations, simply the introduction of them doesn't do the trick. We need to maintain them precisely to be able to gather benefit from their introduction. And this is what I addressed by working on finite difference. The basic idea is that reevaluating formulas. So all instrumentation relations are defined via FOTC, first order logic with transitive closure, formulas over correlations. So hypothetically, it seems like you should update the core predicates in the structure to reflect the effect of the statement, and then recompute instrumentation relations based on their formulas, right? It might work. For example, here we have a structure that represents a concrete list of length 3. And suppose we want to reflect the effect of assignment x gets x dot n, meaning we're moving one step forward. Well, we can simply recompute this formula, definition of R sub x, the reachability from x, for every assignment to v, and we'll get the following values. This guy is no longer reachable, the other two are reachable. Not surprising. The problem comes in when we have abstract structures. This structure represents all lists of length 2 or longer. If we're trying to reflect the effect of statement x gets x dot n, we need to consider two possibilities, that there are exactly 2 elements or 3 or more. This is what's known as the focus step, as some of you are familiar with that. And if we simply compute R sub x for all assignments to v in these two structures, here's what we get. Look at that little 1/2. Seems like we shouldn't be getting a 1/2. Just because we're moving one step closer to this node, it shouldn't become unreachable, possibly, if it was reachable at the start, right? Why is it becoming 1/2? Well, if we simply compute this in the new structure, say x points to, so v prime bound to this will give us x of v prime equal 1. And then n star, we're trying to do the n star across this 1/2 edge. The best we can do is 1/2. So that's why the computation will lead to 1/2. But really, we know better than that. We know it should be a 1. It used to be reachable. It should stay reachable. How can we do this? Well, we can do this by having an incremental update. An update we can compute in the old structure. It says that the new value, R sub x new, will be true if in the old structure the node v is reachable from x and is not the one being pointed to by x. So we're saying that the nodes that corresponding to those that used to be pointed to by x become unreachable. All other ones are still reachable. Does that make sense? So we're incrementally computing it based on the values in the old structure. Now, in the past, the user had to provide all update formulas manually. This was a lot of work. This was very error prone. I remember fixing one update for one transitive closure formula 4 times and kept finding some subtle issues. And that formula had been used in TVLA for 2 years by then already. And of course, it precludes automatic abstraction refinement. If you introduce some complicated new instrumentation relation that you'd like to track, what are you going to do? Throw it back to the user, say, well, now provide me a safe update formula. It's very, very hard. So the solution is this finite differencing of formulas, which can be viewed as follows. Suppose we have a unary relation. It doesn't really matter what the arity is. Just for clarity, suppose we have a unary relation P of V. The new values depend on the old values. If P held for binding to V at the start, it will continue to hold if there is no negative change, defined with this negative difference formula. So delta minus says, well, it defines a negative change in relation P affected by statement ST. And then if it used to be false, then it will start being true if there's a positive difference, a positive change delta plus. And we call this an update formula. Pictorially, if this is the universe of individuals for which P holds, we first take out those for which delta minus holds. Then we add in those for which delta plus holds, and this is our new the new set of individuals for which P holds in the new structure. So conceptually, here's what's happening. We have a structure S that has only core information that's been updated by a core update tau to obtain S prime. Sometime back, we obtained precise values for our instrumentation relation P, and it's stored here via its definition, psi sub P. What we're trying to do now is, instead of recomputing the definition from the updated structure, we want to use the precise answers we had, the definition, and the update to core relations, which are constituents of this definition, to synthesize a more precise new value. And what does this remind you of? Or it at least reminds me of database view maintenance. The problem is you have a database, you have an update U, and you obtain a modified database. Sometime back, you computed a query phi that yielded you a view V. Now, in database view maintenance, the problem is you want to avoid recomputation, and you want to synthesize the answer from the old answer, the definition of the view, and the update to the underlying database. The very same setting, the very same problem, but a different setting because they simply want to avoid recomputing to speed up their operation. For us, we'll lose precision. So recomputation is not an option because we will lose information. As I showed you with the R sub x predicate, we cannot recompute reachability, for example, precisely. So for us, it's not simply an optimization. We have to do this to maintain precision. And if we have time, I can show. So how does this actually help? First, we know that the right, it's crucial to find the right abstraction to be able to verify the problem. And abstraction in our setting is defined by instrumentation relations. And whenever you introduce a new instrumentation relation, for maintaining it precisely, you have to have an automatic method of obtaining these transformers or update formulas. And an additional benefit is that FD, finite differencing, is guaranteed to produce correct formulas, correct updates. So they may be imprecise, but they'll never give a wrong answer. They're always safe. And I have 2 slides on just one example of how it works like for transitive closure, but I can skip those. They're kind of detailed. So I can stop here, or I can show 2 slides. Okay. Yes. Mm-hmm. Right. So the 2. Maybe I can. Yeah. The input is a program, in a sort of program. So it's whatever 10 lines of C code or something like that. It is also normally you have 2 ways of defining input to the program. You can either write down a 3-value logical structure, or something that I provided recently is a automatic way, a non-deterministic small routine that automatically constructs all valid inputs. And the analysis so it's a small snippet of C code with some non-determinism, and the analysis of it by TVLA produces the right three-valued structures that should be at input. So it's kind of, you can think of it as closing the environment, similar to work on Godefroy's work and Alexander Tkachuk's work. So you have a small snippet, you have the code itself, you have a small snippet that creates all possible inputs, and you write down the query that you want to hold. And the query for insert sort was what I showed, that for all v1, v2, if v1 and v2 have equal data values and v1 precedes v2, then v1 will precede v2 at the end. And then the query, I have no in first order logic. Just basically the way you saw it for all v1, v2, DLE v1, v2, and DLE v2, v1, and Tn v1, v2 implies Tn0 v1, v2. I left a zero sum. Simple first order logic queries. And it's yes. And I quantify overall nodes. So it's kind of, in a sense, it's the most natural description, because when you're talking about the heap, really you want to be able to quantify over the objects in the heap. You don't need to think about the abstraction. There's a fundamental theorem called the Embedding Theorem that guarantees that anything you write down in first order logic with transitive closure, any question, any answer you get back from TVLA will always be safe. So there is no restriction on what you can write down. You may have imprecise answers, but there's no restriction on what you can write down, and so you always think in the concrete instead of thinking in the abstract. And that's another great benefit of the tool, of this framework in general, that you don't need to think in terms of abstract values. Just think, okay, what do I want to do? I'm talking about sorting. Okay, well, for any pair of nodes, if one is a successor of the other, then the first one is less than or equal to the second one. It's a two literal formula. So I feel it's a very natural way to specify things. And so then when the tool works, it gets an indefinite answer to the query pretty quickly, and it figures out that there's some abstraction steps that are losing information by showing that some abstraction steps combine zeros and ones, and so it's fully automatic. It says, yes, at this point we have an information loss point. It applies inductive logic programming, finds some formulas that are candidates, and then tries to carry these formulas forward to see if a subsequent step will benefit from their introduction. So in a subsequent step, when we pull apart the nodes that U2, U3 represents, whether we'll all of a sudden have more precision than we used to. If so, chances are this is useful, throw it in, start a new iteration. And so something like maybe 30 seconds later, it says for sure insert sort as a stable sort with those inputs. Yes, I think Sumit was first. Mm-hmm. Mm-hmm. If all the if you give all the right instrumentation relations, then sure. Oh yeah, absolutely. That's not an issue. So given the right node distinctions, given the right instrumentation relations, all the, so to speak, invariants will be synthesized automatically by TVLA by examining an abstract interpretation. At the end, will say, yes, there's the following combination of these things that holds for the following subgroups of nodes, and so the important part is to define the right distinctions among nodes, and then the Boolean combinations and. Right. Right. So if the user specifies the right instrumentation relations, then it will be sufficient to verify the property if the property is some combination of those relations. Yes. Yes, sir. Mm-hmm. 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 No, I have not tried to do it. That's an excellent question. I have not tried to do it in part because as you saw, it's a pretty huge state space. So, but if I'm applying my algorithm to a DAG, I have some finite amount of sharing, right? So meaning that between every pair of nodes, there is some bound on the number of ways you can reach from one node to the other. In a tree, there's one path, at most one path, from any node to any other node, right? In a DAG, right. Right, basically, yes. Right, if I remove these assumptions, then, so what I'm saying is that if I remove these assumptions, then first of all, the algorithm behaves a little bit differently because for every node that can be reached multiple ways because of some sharing, so suppose there are 2 paths to a given node from, say, the root. Then it will be visited instead of 3 times, it will be visited 6 times. So there's this, so first of all, there's a different behavior on such a thing. But, and it will certainly blow up my state space significantly. And so, to the correctness, No. The algorithm, so the algorithm that I'm using is correct for binary trees and binary trees with sharing, meaning DAGs. This particular algorithm, so there's a whole wealth of these algorithms that are related, all basically do some pointer rotation or reversal. This algorithm works on binary trees and binary trees with sharing, meaning DAGs. It does not work on trees, on graphs with cycles. And what it does is, unlike what you might imagine, it does not go into an infinite cycle. It simply does not complete the traversal, meaning that it leaves some edges perturbed. There are some other algorithms, and to the best knowledge of everyone involved, you have to have at least tag bits or something. You cannot have a purely constant space algorithm. But some other algorithms allow you to perform a complete traversal and restoration of any graph whatsoever. And so there's a whole wealth of these different things. This one will work correctly on DAGs. Otherwise, yes, I will produce, if it doesn't on something, yes, it will produce, say, well, this is false here, and it can unwrap the steps that you took and say, okay, well, on this path, here's a counterexample to how you will go wrong, and this is a particular tree or the thing that will fail on.
So for the void code for weight algorithm, did you use this abstraction framework?
No, actually, so the 3 or the 6 key relations I introduced by hand, and I can learn them via ILP, but because it's such a vast state space, I have to do a lot of optimization to try to get it to fit it in. So for now, it's done automatically, but they have the exact form that ILP standardly learns, so I shouldn't have any problems with automating that last remaining step as well. Right. So it's kind of, you can think of the basic difference is I'm doing, maybe I can call it an ILGAR, information loss guided abstraction refinement, as opposed to CGAR, counterexample guided. And so it's, so it's not as closely tied to the property being verified. And so I have to build in some heuristics to try to keep my feet on the ground and not learn all kinds of useless things like DLE or not DLE, et cetera, et cetera. So yeah, it's a good point, but it's still it's a powerful technique for learning whenever you do lose information, learning whatever information you're losing. And so that's in that sense more powerful. And how are we doing on time? Submit, yeah. There are certainly, well, so the first question will answer the second to some degree, meaning that the largest programs that I've applied it to are, usually they're still, for the most part, fairly small toy programs. The bad thing is that TVLA, if every single statement has some effect on the heap, then usually you don't, you can't really handle giant things unless they're really disconnected. There's some behavior that doesn't interfere with some. But basically, if every statement has some direct effect on what's being manipulated, and every statement has some interaction with other statements, you can't really scale this too much. It's a complex technique on the one hand. On the other hand, in most reasonable programs, there's very little of the program that actually deals with a heap. It's not like you can have this, a whole giant program filled with Deutscher weight style statements that are all interfering with each other. And so that's why I'm actually looking into the direction of trying to snap out modules that are independent of all other code and manipulate some kind of an enclosed data structure. So that's why I'm trying to move in the direction of using slicing and other techniques to get these out of real code. And in terms of what's not good about it is, well, one is that scalability is a bit of an issue, and so you have to perform abstraction, or you have to find small pieces of the program to work on. And learning can learn a lot of things. You know, ILP can learn a lot of things, but at the same time, in the sense that it's not very limited by the language. There's no limit on the syntax of what can be learned. But at the same time, there are so many variables in terms of what examples you provide, what's available, et cetera, that it's very hard to know when you can and when you cannot learn a formula that is useful for you. It searches such a vast state space that you're not sure if it'll get distracted on something that is not very important. So I have yet to really understand very thoroughly exactly when learning is sufficient to verify an arbitrary property and when it's not. But in general, it's a very hard question because of so many inputs into the ILP algorithm. Okay. Thank you all very much for